Thank you for being here. I know it's after lunch. Probably you're sitting in a very comfortable chair in a cinema, and I don't want to bore you. I promise it's going to be entertaining. We're going to talk about feature stores, feature platforms, machine learning, and what we discovered, what we learned, what failed, and we're happy to share that with you here. Let me start. I need to do this. I need to explain a bit the context, which is what IGN does. Chances are that you have used, say, Netflix or an Uber or a Glovo or something like that. We are the company that processed that payment that happened there, right? There are a few things in the culture of the company and how we are set up that have implications in how we have designed feature stores and features platforms. First of all, we are headquartered in Amsterdam, but we are actually worldwide. We service the whole world everywhere. And we serviced around, last year in 2022, we processed around $100 billion in volume, a billion being thousands of millions. In Spanish, it's a bit different, which is a lot. I think the important mapping there is to see how many requests that means to our APIs and services, right? Also, a quick intro on me and why am I here speaking about this. I'm this guy. I'm actually born and raised in Mallorca. I'm Spanish. I know that's not an eyebrow raiser in Spain, but in the north of Europe where I live, people think that we're still running around in a coconut tree. I studied telecoms. I had a career in aerospace, and then I joined IGN, where I used my time in the data team, building machine learning systems and everything data platform and everything, right? And again, we're talking about features and feature platforms and feature stores and machine learning systems, but we need to start, as we say in the company, we build with our users, we need to start with the use cases. Why do we want machine learning at all? And why do we want features to feed those machine learning systems at all, right? So let me guide you here through payment journey, right? So imagine you're there just buying a flight somewhere, you put your credit card details, right? And then at the moment we receive this request, and we receive that payment, and then the first thing we do is we hit the service and say, okay, is this legit or is this fraud? So we try to discern whether we want to process this transaction or we want to stop it and say, I don't know, it's too hot, right? So in case we want to do this, then we go to another service where we call it the first attempt, and this is where we kind of pose the transaction to be successful when we hit the environment that we call it, which is basically networks containing, you can think of Visa, MasterCard, and other players, JCB, MX, whatever, and all the issuers, all the banks of the world, right? From there on, we want to authorize a transaction, but if it didn't happen, if there was some friction, then we learn something, so we can condition our second attempt to be even more successful. Now, you see at the top there's an arrow with an lightning emoji there. That means that it happens very fast. It happens with, we have an SLA of around 1 second, right? So you want your payments to be fast because otherwise it's a very poor shopper experience. That means conversion drop-off and things like that. That's one of our USPs. We also have other systems like auto rescue, which is more like when do we want to schedule, for example, a subscription. Like when you pay for your Netflix, there's some logic in there, right? That's more timed. Now, what many people don't know when they buy their flights online is that those things, those green boxes there, they contain behind a machine learning model, right? So we have a lot of data, and we can learn from that data and automate the decisioning, for example, to decide whether a transaction is too risky or is not risky enough and we want to continue, right? So revisiting that flow, we started with a risk service. We say, yeah, I want to do this, I don't want to do that. We have a machine learning model that we have deployed that tells us the likelihood of fraud. And then we have another machine learning model following to that, which we call authentication engine, which decides whether, you know, if we're not so sure, we might want to authenticate you, so introduce some friction to make sure that you are who you actually are. You are, for example, the owner of that credit card. And also how, right? There's many ways. So how can we do that, balancing the risk and balancing the friction that we are putting in the flow, right? Then we have Pathfinder, which is another service, ML-based, that does routing and does a number of optimizations to maximize the probability of success when we hit the issuer network and the schemes. And again, if it failed, then we learn something, and then we can condition all this process and optimize for a different target in order to make another successful or another attempt to be successful, right? Again, Unretriever, that's the other service there, is also ML-based. To give you a sense of the scale we operate, these little robots serve around 300 billion requests per year. That means that we have around 1,000 TPS, transactions requests per second, with a latency of 100 milliseconds. And why we do that? Why do we go through the enormous operational complexity of all this ML ops gig? Well, 4% conversion uplift. Now, 4% doesn't seem a lot, but when you multiply that by $800 billion, then it actually makes kind of sense that we do this, right? Also important to know on our machine learning proposal is that the models need to have awareness of each other. That has more implications around how we train them, right? And also, we run them and we deploy them through our experimentation framework. We constantly run A/B tests with different strategies on different machine learning models, also to harness the risk behind it, right? Now, how do you train and how do you deploy all this, right? What is the flow here, right? So that's an important concept at Adyen. We have two separate platforms. We have one platform, actually, that exposes all these APIs endpoints to the world for transaction processing and refunds and payouts and KYC details and whatnot. And then we have another platform, which we call the big data platform, that is more around offline flows, the classical, you can imagine, Apache stack with Hadoop and Spark and all this computing, right? So all these events, all this data flowing from these transactions eventually flows into the big data platform, and from there on we do ETL or ELT, pick the one you want. And our data is mostly transactional, right? So in the end, we end up having tables or graphs. There's a lot of things around, okay, you shop here, you shop there, from this merchant there and there and that. So we can use that as well as an intellect. I'll more on that later. And then we train our models in the platform, right? That's where they learn. And we can also score those models in the platform offline. And the reduced product of it is signals or some alerts or whatever it is, but the output of the model. But that's the offline flow. What about the online flow? Then we take those robots, we take those artifacts, and we deploy them into our main platform, right? So when we hit those risk services or authentication services, then there is an artifact ready to be deployed and to serve an inference answer on this. A stop there as well on the complexity of the features that can go there. Think about graphs, right? This is just some exercise we did some time ago. We are exploring a lot of the data points coming from a classical view of thinking as tables, transactions being rows, to this mapping around networks and graphs and this texture where we can derive a lot of information that is very useful for machine learning, right? So, okay, we did that, and we started working with this. And to do this, you need a feature store, right? You need to feed those machine learning models either with at training time or at scoring time. You also need to serve them features, right? So we compiled a requirements list as engineers, of course. That's where we started. Because I live in the Netherlands, we call it the Sinterklaas lijstje. It's a bit of trivia. There's no Santa Claus there. There's another guy that comes 1 month before from Spain by boat, from Madrid. So that's interesting. But I'll call it here La Carta a los Reyes because we are in Spain, and I think that we can just go with Queridos Reyes Magos, right? So what do we want out from a feature store? We want feature parity, super important, right? We want that the data that we train on is the same as the data we score on when these artifacts are deployed. If there is an imbalance there, that can create some weird effects in our decisioning, and because it's automated, it can go very bad. So that's one, feature parity. Another one, latency. Right? So if you have an SLA of, say, 100 milliseconds for that ML inference request, then better be quick as well when retrieving the features, right? What about the recency of the features, right? So you compute those features, you deploy them, or you compute them somewhere else. How old were they, right? It's important as well that the features stay fresh. Otherwise, you're making outdated predictions, right? Another one is the cardinality of our data set. How many keys are we supporting? And then some people will be like, oh, you know, this much. We are thinking about on the order of billions. So that's another requirement there that we need to factor. remember, I started explaining a bit of the company and the footprint and all that. Well, it's important that it's distributed. So we have worldwide distributed data centers, and that is there. So it doesn't matter if you're eating a baguette or burger or rice, you need to have a feature store available there for you 24 hours, just like Spider-Man. And what else? What else? There's more. It needs to fit a lot of data. We think in terabytes here, right? So it needs to fit all the data. And also, because you want data scientists to actually love that feature store and not hate it, you want to be able to accommodate for complex features and feature diversity and self-service computation, right? So data scientists, you know, these are the data scientists, they keep forgetting that probably they scrap better performance not out of doing deep, complex models, but it's very fancy, neither doing fine-tuning of models, but actually carving better features, right? But in today's world, probably they're just using ChatGPT because everyone does that today. Anyway, Carta a los Reyes, back here, these are all the things that we want out of a feature platform, which is a lot, isn't it? Okay, but I said we do have our transaction flows already equipped with machine learning. So what happens? What do we have now? Well, we started building stuff, and we started using what we had, as we do, and upgrading what we had, and operating what we had, and then thinking about what it falls short and what we need to build next. So let's start, for example, with an example of the risk request, right? So there is this service or application called the PAL. It's jargon for payments, called Payment Authorization Layer, that basically has a call to this risk service. And this risk service contacts these different data sources. We have a velocity database, and the velocity database runs on Postgres and does all these fast and recent calculations. For example, how many times in the last minute has this credit card been used, right? That's something very fresh, very fast that you need to have there. I skip a second to the far right. Lookup tables, that's very simple. Is this, for example, this credit card or this detail somehow stored in another list that tells me we know it's fraudulent, for example, right? So you just want to look it up. Okay. And then we also have, also Postgres, by the way, and then we also have Shopper DNA, which is actually a product that we have from Adyen that runs on Postgres, important detail, and tries to derive complex features, right? So let me, oh, clicker died. All right, so there it is. So let me zoom in for a second in Shopper DNA. This is the visualization on the, in the application where you zoom in and then you see all these details aggregated. What it does is basically it's a smart logic over Postgres in real time where you do aggregations and then you start creating merging of identifiers, right? Of different details that say, okay, hang on a second, same address, same email, same bank account, and you start creating these profiles, right? We call them shoppers. In network science, that's called community detection, but we just do it very fast over Postgres, which is good because it supports the flows and the scale that we had at some point. It has a consistency read-write lock, but still, so allows us to have this consistency, but still we have real-time performance. The big cons are definitely scalability, because you can get this far with Postgres, and also the complexity and the flexibility on the different algorithms and merging strategies that we can. So basically, community detections plus, right? If you're interested, you can just go and read this blog post about how Postgres can effectively be somehow useful graph database. Yeah, if you scan the QR code, I think it's big enough, isn't it? Then you can get more details around this. But coming back to that flow, we still had something missing, right? We still had these sources. We had velocity, we have shopper, and we had lookup tables. And then at some point we thought, hang on a second, we can actually boost machine learning performance if we have another type of features. Features that are maybe a bit more complex to compute. Things about rates and maybe, I don't know, things more complex than just a number. That have medium cardinality, thinking about here, for example, 100K to 1 million, and that has low frequency, so things that might change over the course of a day, but not in the last 10 seconds, right? As an example, just to keep a bit here and to really ground it, this is an example feature of this type, the first approved rate performance per bin, which is the bank identification number, so every little color that you see here is one key with one number per day, right? And this is what we want to store there. The cardinality of this set is around 200K. We had nowhere to store this. It didn't fit velocity, it didn't fit shopper, it didn't fit a lookup table. So where do we put them and how do we compute it, right? And we thought, I know how to do this. Remember, we had the big data platform, right? So we can use and leverage the stack that we have in the big data platform, which is the well-known Apache Spark and Airflow. And then we're going to use an open source package called Feast. You might have heard of it, or you might have not heard of it, but Feast is a feature store open source package. Right? I'll go more into details about it, but effectively allows you to define your features in there, right? So then the ETLs and ELT flows in the big data platforms will compute the features. And at this point, they live in the big data platforms, stored in Parquet files with a Hive meta store on top, whatever. And then we can just beam them up to the feature store in the online flow, which is a Postgres instance, right? So it just picks up the files, ingests them, there you go. So you have a nice now fourth data source to store and to serve the features with that nature. And then, of course, the artifacts are trained with that data as well. We deploy them in the risk scoring system. Good stuff, right? At this point, we're pretty satisfied, but something wasn't clicking, right? So if we take an honest look, yeah, we cannot really say we have a feature store, right? We have a bit of a Frankenstein of things that actually works, but with some sort of runway. And we want to build for the future. What we say is we build for 20x. That's kind of our mental rule. So we went back to the Carta de los Reyes Magos, and we started looking at, okay, how good are we there, right? And we started saying that indeed, some of the things were okay, some other things were like, and some other things were just like, yeah, that's not happening, right? So things like self-serving computing of features, I was like, such a mess to compute features, it's not easy, right? Storage and scalability, everything running on Postgres, it will get you this far, right? The recency, well, if all these complex features, we just update them once a day, then it's not gonna be very fresh, right? So we gathered again and we said, okay, we need to build something else. We need to build a proper feature store. And this is where we said, we are going to do a blueprint. We're going to build something that actually serves us for the future as far as we can see. But then we stopped there for a second and we said, do we want to build a feature store or do we want to build a feature platform? And there was a lot of debate about the jargon. Like, is that a feature engineering platform? Is that a feature store? What is this, right? So we did a little research and we ended up in feature platform because a feature store indeed stores features. It could be quite pointless if a feature store wouldn't store features, right? It serves the features in an online flow, but it doesn't compute the features, right? While the feature platform computes the features. That was where we draw the line, and then we were happy to see resources on the internet, like this great blog post from Chip Huyen, which is someone that writes very good stuff around machine learning, and wrote this blog post, and that gives us the confidence, like, okay, we're on the right track. This is what we want to build, right? We're not just going completely off track from the world. So what's the blueprint? This is the blueprint. Now, I have a big box called feature platform, and then inside you can see that you have an online flow and an offline flow somehow bridged together, right? You still have a computing engine layer on both sides, and you have a feature definition layer that locks them up to make sure that there's feature parity. And there's also feature monitoring because, well, if something goes wrong, you want to know as soon as possible and start with the features, right? And then this, for me at least, was a bit of a mental twist. Feature platform is not something that lives in one place. It's something that lives in two places. Because indeed, you train and you might even score machine learning models in the big data platform, offline, batches even, but then you deploy them in an online platform. So the feature platform needs to live in the two spaces simultaneously, and it needs to be consistent, right? So I'll give you a bit of an example here. Let's see what happens when you want to compute start moving features. Think the velocity checks I talked before, right? Like how many times has this credit card been used in the last 10 minutes, right? So this is a start, it's a moving, fast-moving feature, right? So you need to have a computing engine there, and honest emoji there. We are considering Flink, Apache Flink, as a streaming computing engine. But we have decided on our hot storage layer, which is Cassandra. And I'll go later on why we chose for Cassandra. If instead you have a slow-moving feature, think about that, read, rate, approve, bin, whatever thing, then we compute it in Spark, super flexible, super known. And then we store it in our cold storage systems, right? Which basically our big data platform, Hadoop, Parquet files, whatever. And they sync up. That's important, right? So whatever you compute in the hot storage through Flink, then you give it back to cold storage. And whatever you compute through the cold storage, you give it back to the hot storage. What is the difference, of course, is that in the hot storage, you only need to store the stuff that you're going to need for the machine learning model that you have deployed. So probably you don't need data from 5 years ago, but you want to store it in the cold storage, right? And then we use Feast as the glue to make sure that the feature definition is actually binding both flows, right? For feature monitoring, there's another, I was about to say feature, but it becomes a bit complex, but another side of the thing is, we're still considering packages there, but Boxkite could be quite a good one. Now, where does it feed in the whole picture, all this? If we look back at the MLOps space, right? MLOps, this fancy concept, maybe not so much anymore, maybe 1 year ago, 2 years ago, but MLOps basically says, well, you need to have features, right? You need to serve them as well. You need to serve and deploy models, and then you need to monitor, right? And so if we have at the core, at the center, we have this feature platform, then we're solving for the feature computation, and we're solving for the feature serving and storage, obviously. And then there is this consistency going through the ML artifacts that we deploy, that we train on our big data platform, that we deploy in our online processing system. And then we need to add, of course, a monitoring observability suite on top of our automated decisioning, which we have right now with Elastic and Grafana, right? I said before we chose Cassandra, right? And I said it like, yeah, whatever, Cassandra is good, right? But why did we choose Cassandra, right? We actually took some time to investigate what we needed to do next, because when you choose this technology and you are operating at the scale that we are and with all the regulation that we have on top, at the end of the day, we touch a lot of money flowing here. So we need to make sure about our choices. And we chose Cassandra. We have a tech-rated process, and then we evaluated different candidates, right? We ended up benchmarking those 4, Postgres, Cockroach, Redis, and Cassandra. Pros and cons on each of them. But probably Postgres is what we had that didn't work, so we have to move on from that one, clear. From Cockroach, what we didn't like is that it bets a lot on consistency. So you have a write and read lock that compromises speed. So we prefer to have speed, which is probably what Cassandra gives you. And Redis, well, the problem we have there mostly is that it's cached in memory, so you can put a lot of data, but it's going to be very expensive. So we believe that with our blueprint, running with the tech choices that we have made, then we are all green in our requirement sheet, right? Yeah, we believe so. Another thing to say is, why did we just build and blueprinted this instead of just going and just getting something from the open source, for example, community? So we did that, actually. We evaluated that, right? We have this process we call ADR, which is an any decision record. So when a bunch of engineers decide on something, we make sure that we write it down and we make it available for everyone to understand why the train of thought and what happened here and there, and then they can know, okay, that's why we chose Cassandra, right? So for the feature store package, though, we were considering 2 main contenders here. Feast, which we were already using partially for feature definition, and Feather. And Feather, I'll get there, we chose for Feast, surprise, I said it before. But why didn't we choose Feather? Feather is a package that is open source, indeed, but it's developed by LinkedIn and is very LinkedIn. It has a lot of things and choices that are reflecting what the company wants and for their use case. Not surprising, for example, a lot of things are very easy if you're running on Azure. But if you're running on a different cloud, then it might begin to be too picky. Feast, instead, is way more open, but that's a bit the trade-off when you're using an engineering tool. If it's very generic, then you probably are compromising on power. So in the end, we chose for Feast, and we believe that with this blueprint, right, with these technologies here, then we will get to the next stage of machine learning. That's where we want to be. And another thing I want to say is that a lot of these things are built, but a lot of others aren't. We're still building that. And we need to build that and keep the trains running when we're still swapping those services. So we're building a team in Madrid to help us build this thing, right? So we're hiring. We don't do that in the Netherlands. That's, by the way, Dutch food. If you don't know this, good for you. You shouldn't know it. It's called frikandel, and it's not good. But if you don't like that, don't worry. We have a team in Madrid, so we're also hiring in Madrid, right? And then, yeah, that's the end of my presentation. I have a team with me today that are also experts in feature platforms. So if you want to if you have some really technical questions and you want to engage in a sweaty debate around choices and around architectures and whatever, they are the ones you should speak to. Otherwise, yeah, again, my name is Andreu. I just want to say gracias for being here. And now I think we have plenty of time. If you have questions, I'm happy to answer them. Yeah. Thank you. There's a question there.
Well, thank you for your presentation. I have two questions, very basic ones. The first one is that infrastructure that you presented, is it on-premise?
It is on-prem.
It is not on cloud. And
no.
Are you using a distribution, a paid distribution of Hadoop or like Cloudera or Hortonworks, or are you maintaining it all by yourselves?
Yeah. So short questions is yes, it's on-prem using the Hortonworks distribution. Mm-hmm. Yeah. So the reason we on-prem, I can go into that if you want, because people are like, oh, you're running on-prem, why? I
share your pain.
Yeah. I think before we had the whole data gig in Adyen is a backend company, right? It's pumping payments and making sure they go through, right? And that's basically backend. And then they were like, okay, we can do that. We don't need to go through the cloud. Also, we're storing very sensitive data, so there's a lot of requirements around the personal identifiable data, regulation, PCI, whatnot. And we're like, okay, I want to do it. Also, we have a strong preference for being in control. Like everything we do, we try to do it ourselves or use open source. Just because we don't want to give away control, right? If, for example, if something fails or you want to iterate very fast on something, you don't need to have a dependency on a partner or on a vendor in order to fix an issue or to, for example, develop a new feature or whatever it is, right? And from there on, I think that on the big data side, we just started a bit with the same philosophy. But I think it's important as well to know that Adyen is a company that even, started more like some 10, 15 years ago. It was always thought to be in the long term, right? So if you're building for the long term and you're really aiming for processing trillions of dollars or years a year, probably you want to invest in your own tech stack and your own functionality and not depend from, for example, cloud provider, even from the cost perspective, right? Now, having said that, one thing is that you run on cloud, which means someone else's data center. Another thing is that you don't use cloud practices, right? So in terms of autonomy and deployments, it should be easy. It shouldn't be like, yeah, okay, I need to go to MediaMarkt and buy a new computer and then plug it and then, okay, I have a new node, right? No, it's not like that. There's more practice that we build up through years.
Thank you.
Cheers. I think we're good. We have time. Speak now or never. Yeah, I think we can call it today. Thank you very much, everyone, for being here.